All right, can you guys hear me? Sure, looks like. All right, we are already 9 minutes late, so I'll try to make sure that we are maybe able to get on time. So I'm Vishal. I work for MSRC Engineering and Microsoft. Now I just want to picture where do I belong to in this whole ecosystem of security. And if you ever find a bug in Microsoft and you figure out, hey, I want to send it to Microsoft, we are the guys who are at the receiving end. So we are the first guys who handle your bugs and then transfer it to the product teams. So yeah, so if you have any grievances around these communications, feel free to reach out to me during this conference, or I have a Twitter handle if you want to reach out to me there as well. I started leading the response team there, so I'll probably be able to speak more from that stand. Don't worry about anything. Now coming back to this talk, if you have never heard about Win32k, don't worry about it. I'll touch up a little bit about it so that everybody's on the same page. But just in case, I want to make sure that this is absolutely clear, because if you are not sure what Win32k is, this presentation is going to sound totally absurd. Win32k is the most famous kernel driver in Windows world, and for the right reasons. And you will know about it as I go through the presentations. This talk is about going into details about, hey, why is that the case? Why is it such an infamous driver? And what have we done to take this beast head on? So there are some learnings, some challenges that we face, which is going to be interesting for you guys. A couple of key takeaways if you want to really go back after looking at this whole presentations. One, things are tough. Security is very hard problem to solve. The regular technical problem is also pretty hard itself. So security obviously is on top of all that stuff. So when you look at securities from that perspective, then obviously you start blabbering about, hey, okay, security is hard. Should I even try to solve this? This presentation might actually help you in identifying, yes, it is hard, but it's not unsolvable. There are complex problems which can be solved, and this is one of the experience that probably gonna sail you through. Another interesting is we have added some very cool mitigations in the system. Some of that might apply to your environment, not in the exact same way, but that would be some learning you can take back and see if that applies to your environment and apply some of those. With that, let's very simple agenda, straightforward. The meat of the presentation is the middle one, where we're going to revisit some of the designs that we have done, or redesigns we have done in this Win32k ecosystem. But to actually get there, you need to have some basics. So the initial stage is to set the stage about, hey, why are we talking about this right now? So the idea is to give you an idea of where does this whole Win32k driver sits into the ecosystem. Why are we talking about Win32k and not 400 other drivers that we have in Windows? So that'll get you started of why this particular driver makes significance. And then we'll conclude with, hey, what is the next step we are doing? What did we learn from this experience? Where are we right now? And what do we think from security community perspective is the next target we want to go after? Because realistically, this is just the beginning of another story. All right, so with that, let's take a look at typical vulnerability or an exploit that has been written in Windows world. And this is from the perspective of, say, Edge. And why I'm taking Edge as an example, because that's the most common attack vector. That's how you get in on Windows boxes. Now, to take in perspective, things have changed over the years. It's not the same XP word where, hey, okay, I found a stack overrun. Let me just, because I now have everything, let me just run this and we are done. Nope, doesn't work anymore. So you have to do a lot more. Your exploit may actually span multiple components, may require multiple vulnerabilities. And when I say that, this will give you a good idea of the first goal for you as an attacker, whenever you're picking a target, is to actually get something running on your attacker, on your victim's boxes, right? So what would you do first? Probably one of the prime example is pass on a HTML link to somebody, like a link to a web page. Somebody opens that, and voila, he's running his code on your boxes now. And the interesting aspect to it is, what you would have probably find is a memory corruption, which is one of the cogs in the whole machinery. But that's just one piece of action that you're looking for. There are 4 more, or maybe multiple more actions, or multiple cogs that you need to generate to actually end up doing a code execution on the browser. And all these cogs we are talking about are the various mitigations that have been added into the system, which makes your exploitation a little more difficult now. You might actually end up with a very powerful primitive, which may actually give you a strong enough primitive, which will make all the cogs run in the one shot with that same primitive itself. But that doesn't mean your exploit should not already be aware of it. So when you write in exploits, you still have to think about all these different mitigations, or you have to still come up with these cogs to work around your stuff. Having said that, once you get the code running on the box, there is something called, which in recent years browsers have introduced, a concept of sandboxing, which means that even if somebody end up clicking your vulnerable link and end up running some code because of all the stuff that you have done, at the end of the day, you still are not getting enough. The reason is because your code is still running inside a very constructive environment, which doesn't allow you to do anything. Like, it doesn't allow you to open sockets, so you won't have a C2C connection open to your servers. So which means you can't do actually pretty much. You're pretty much at this point just running a code inside a binary space, and you're not allowed to go outside that space. So obviously that's not enough. So that's why you need to get out of that sandbox. One of the way people do it is actually get into the kernel. And when you get to the kernel, then you completely own the system, and which is where our second payload comes into the picture. This is the second stage of your exploit, which talks about, hey, okay, how do I do the sandbox escape? So because I was in sandbox, but I want to get out, and I use kernel to do that. Now, interestingly, the same logics apply in like the way it applied in the browser world. Even if you have a memory corruption bug, that doesn't mean you have the exploitation running. You still have to bypass the other mitigations in place. So there are more cogs you need to work around. So in and all, what I'm trying to get to is you have a complex machinery now, which you have to connect all in sync to somehow make the connection from getting a HTML link to end up owning the system. And this is where Win32k comes into picture. So Win32k is one of the kernel driver, which would help you in actually getting to this outside the sandbox. And the two cogs that we were mentioning, where you require to get a code running in the kernel, can be provided by a Win32k code, like the memory corruption bug and the KSLR bypass. We'll touch base on both these things a bit as we go along, so don't stress about if you don't understand any of these cogs, what they're talking about at this point. Now, like I said, there are 400 plus drivers in Windows ecosystem. Why are we talking about Win32k per se? Right? So there would be a very valid question. So I did a statistical analysis on this and said, hey, let's take a look at how many bugs do we get from external world or internally we find those bugs in the Windows ecosystem, and just concerning the kernel drivers at this point. Apparently, Win32k actually constitutes more than 50% of those bugs, which means that this is one driver versus 400 other drivers, and this is still weighing heavy on them. That means there is something definitely funny going around with this driver. And now you need to understand what this driver is to make the complexity more clear. Why do we have so many bugs in this particular driver? So what is Win32k? Well, simply speaking, it's a kernel mode driver. It has two major components inside it. One is to handle the rendering of anything on the screen, which is called the GDI section part of it. And the other part is a user which handles inputs. Like if you click on something, what am I supposed to do? Which window is supposed to do anything? To give a good idea of what these two component does, I'm going to give you a demo. And this is the most fail-proof demo you can come across, because if that fail, which almost did for the first 10 minutes, then my presentation will not work. What you're looking at the screen right now is a demo of that application. And the reason why I say it, because everything you're seeing from font perspective, which is displayed on the screen, is done by that driver. So GDI portion of the driver is responsible for rendering all these fonts on the screen. And apparently, whether it's a full screen or it's not a full screen, it's a Windows property. That property is managed by user, which is dictating what is that supposed to do, like from a Windows perspective. And if I do a click, if I do an X on my keyboard or through a clicker, when you hit the next, that is a message being sent to the window by the Win32k kernel driver saying, hey, you have a message, you have to do some action. And it's upon the application to take the action at this point. But the message is delivered through Win32k.sys. So now you understand, if you remove Win32k.sys from Windows ecosystem, you will end up with just a command prompt. You won't actually see anything else in Windows World. So it is a pretty significant component. And you can imagine, right, okay, if it is that significant, chances of having bugs are higher. Plus it's a complex, very bulky component as well, because it handles everything from user interactions to displaying the fonts and all. Every damn library you can think of which can go wrong is sitting inside it right now. Now, this driver, I actually pulled out something from one of the file in Win32k, and you can see this driver has an entry which says, hey, I'm porting this function from some 3.0 in 1990s. So that makes it older than some of the guys in the audience. And like everything has gone through changes, like we go through changes in our life, this guy has also gone through a lot of changes in its lifetime. One of the the last record change that I could actually come up from, like in my conversation with all the Win32k guys, was this last change. And when I say last change, this is the change that I can actually find documented somewhere. This is before NT4, which I'm talking about 1996. This is before 1996, how Win32k looked like. So there was no Win32k.sys driver on the system. At that time, everything was inside a process called CSRSS. That process still exists today, but just the component we were talking about, the user and GDI component, are not part of that, were part of that basically, the CSRSS process at the time. What we did in NT4 was actually strip down CSRSS, take these two components out from the user mode, moved into kernel, and made it a driver from it. So this was a pretty significant move, and you can imagine why, because we are making so many changes here. I mean, making already it's a bulky code, we are trying to move that code into kernel. That means we are introducing some very interesting aspects of it. Well, let me just go back and talk about, hey, this is 1996. We had very constrained resources. CPU were very, very constrained, and memory was constrained. So the reason why this thing was driven was not because of security, but more from performance perspective. At that time, security was, okay, it was a deal, but not as a big of a focal point. So most of the decisions were taken from, hey, we have to gain a market share. That is the business decision at that point. And we started looking at, hey, how can we actually increase the market share by making this system faster on a slower machines, basically. And how do we make the system faster from moving from user to kernel? If you think about it, because CSRS is a different process on its own, so if a X process wants to send a message to Y process window, it has to actually do context switches now. So it has to go from this process to CSRSS process, and that process then do a context switch to Y process. So there were a lot of context switches happening. And another thing was that CSRSS, since it's a different process, it actually has to spun up new threads. Every time there is a request that comes in from somebody to send a message, a request comes up and it spuns up at that. That's what paired threading is all about. So essentially, all of this were constraining the machine at that point of time. And when we introduced this change, things changed a bit, because now there are no process context switches. You still are doing context switch from user to kernel, but not from user to user, which were more expensive, by the way. So it ended up giving great performance incentive from graphics perspective, which was probably the driver at that point. But moving code from user to kernel has some very unique features. What you need to do now, you have to expose new system calls, because obviously you need an interface between user and kernel to have those interactions going again. We expose something called user mode callback. We'll talk about this again, but this is a very unique feature which was introduced just so that this feature, which when we migrated from user to kernel, can actually work as it is. And then obviously, when you are moving when you're making a driver, there are potentials of making shared memories, shared sections between user and kernel so that they can share the data in case you don't want to transfer it through just, or you couldn't transfer just from the system calls. And there are a bunch more changes, but these are the 3 changes we're going to target as we go in the presentation. And obviously you can think of like all these bigger changes that we are looking at has some security implications. As we go along the presentation, I'm going to discuss about it. But I'm just want to stress at that point, security took a hit in favor of performance. And why does that happen? So as we look at all these 3 changes, which we have seen going through while making these migration from user to kernel, we'll touch base on all these 3 and see how we have tackled this from security standpoint. So now, before I go and jump into this, the idea at this point is, okay, you know that things have gone south from security standpoint when we migrated from user to kernel. And there were some glaring problems from security standpoint. And a couple of years back, like in 2016, we hit a very low period for Win32k.sys when there were like 14 bugs reported in Pwn2 on competition. And it was the worst case scenario for Windows when we looked at every bug, every exploit that was written on Windows had something to do with Win32k.sys. And that point was which was an eye-opener. We already were aware of how bad this component is and how things have gone. But that was like, okay, now this is the worst case. What do we do? We can sit on this and see what happens next year, or we can take some drastic decisions. And at that point, we sit down, looked at all the design. This is where the previous, whatever the design changes you have seen came into picture. And we thought, okay, we know these few areas which were design decision at that point of time. How do we do now? What should we do to make sure that this doesn't stick out to us? And at that point, you still have to understand this, like Windows has few basic pillars, and it sits on those basic pillars. One is, you cannot actually take performance out of it. Whatever is performing today, that's the performance you have to keep sustaining on. I mean, it's very difficult to sell a product if your next version of the product is not going to be same, or at least closer to the performance as the previous one. Another is app compat, which is a huge deal at Microsoft. Especially for Windows, you cannot take app compat risks. Like if some applications like starts breaking because of some dependencies on older operating system, you have to just sustain it, unfortunately. And those are the parallels, and those were the major pillars we still have to comply no matter what redesigning we do in our Windows going forward. So with that in mind, we thought about, okay, let's take the Syscall in consideration for the beginning. So Win32k has over 1100 syscalls. This is twice the size of CentOS, the actual kernel syscalls, which makes it such a huge attack surface. And interestingly, some of the syscalls are more deeper. And when I say deeper, it's like, hey, your system call is just, okay, anti-call one param, which is like just a name for it. And then you pass a parameter. That parameter dictates, okay, what actual system am I supposed to call now? So because that means your system call is just an entry at this point. You are actually going to make more deeper system calls while you actually do the transition further. So 1100 is just a number. It's probably much bigger than the actual surface. So writing code in itself is a hard problem. And now you're asking developers to write secure syscalls, which comes up with its own set of problems. Like you have to take care of all these stuffs that comes with syscalls. If you are not, then think of this. User to kernel is a security boundary, which means that if you find even a single bug in any of the syscall, that means you find a hole which from where you can go from user to kernel. So you have to make sure that every syscall is absolutely 100% secure and has to comply with all the conditions that you are getting in. So like I said, writing code itself is hard. Now you're putting more constraint on it. So obviously it's going to be much more harder. So chances of inducing bugs become just more increasing. So that's why the attack surface just increases drastically. So what do we do? I've given some reference in the title itself. So we do system call filtering. Well, let's hold on for a minute. There is something called no Win32k security policy, which means if as a process, if you enable this policy, then you can say to the system that no matter what I do, if I make a call to Win32k, don't allow it. Basically, it's a hard block to not allow any Win32k system calls. Why does it matter? Chrome, for instance, actually use this feature. And that means if Chrome has a sandbox, like if you end up running some code in the Chrome sandbox, you cannot use Win32k system call to come out of it because it doesn't have any opportunity. That layer doesn't exist for it, which is an awesome feature. Unfortunately, we couldn't use it in Edge. So we had to do something more robust or more different from that perspective. So what we did was, we realized, okay, even though we can actually disconnect Win32k completely from Edge because of a lot more dependency on it, we can still make it filtered out, some of the content which is not needed. So we end up doing, okay, applications don't need all syscalls. So how about we create a subsystems which says, hey, define what syscalls do you want to allow, and everything else, we are not going to allow you to do that. Interestingly, Linux has something much more robust around the same lines, if you have not heard about seccomp, but it does the same thing. For applications, you can allow what system calls you want. It's very, very strong mitigation. So Edge end up using this. We filter out almost 75% of Win32k system calls. Now, there are other components which can also use this feature, which is still Microsoft proprietary at this point. We haven't exposed it to third party yet. What is the impact once we have this enabled? Well, this obviously reduces the attack surface. Previously it was 1100 syscalls, which you can target any one of those. If you find bug on any of the syscall, you can go ahead and exploit it. But now we have constrained it to like, okay, there are only 250 syscalls that you can pass through. It has two implications. One, obviously, you still have to find bug in only those 250 syscalls. Another, when you are actually writing exploits, you have to rely on other functionality of the OS as well. Like you might be relying on some syscall which does pool spraying, right? So there is a cascade effect to it. So if that pool spray API is now being filtered out, so you may be a little more handicapped while writing the exploit itself. And that helps, and we have seen that helping. But does it kill all exploits? Oh, hell no, it doesn't. We have seen exploits, people writing exploits even with that filtration in place, which is awesome to see. But that doesn't mean that this filtering is not significant. It is significant. It increases the exploitation cost substantially because now people have to find bugs only in those filtered out syscalls, and it increases the cost as such. All right, so another major piece was user mode callback. Now this is something that I want to really touch base on because this is very unique. You wouldn't probably see in any other system. It would be interesting to know how and why does it needed. It is a side effect of all redesign and designing that I've gone through in Win32k history. So it'll be interesting to see why we had it in the first place and why it is really needed by us and why we can actually get away from it. So what is it? So let's take a look at this diagram which talks about, hey, you have a user mode and kernel mode and there is a boundary in between. Here is a process which wants to destroy a window, for instance. So it makes a Win32 API call, which is a user mode destroy window call. On the right side, I'm showing a call stack, which gonna signify, hey, how my calls are going on. So when you make this call, you make a transition to kernel. Now, for simplicity, there are transition functions when you actually make from user mode to kernel. I'm actually just omitting this for now because it's not needed. What is important is you made a user mode some functionality call and then which end up calling a system call. And on the call stack, you can see both being transitioned. Now, at this point, this function call is supposed to destroy the window, which is just an object in the memory. But apparently, there is something interesting here. Now what Windows does is, it gives application an opportunity to do something extra. It's saying, hey, why I'm destroying this window, let me go back to the application, and the application decide whether it wants to do anything at this point. For instance, maybe you want to save something which is there on the window, like create a log out of it or something. So basically it is making you, the application, aware that, hey, I'm going to destroy this window. Is there anything you want to do? And this is where the user mode callbacks comes into picture. This is very interesting because what we are doing right now is we are doing something called reverse syscalls. We are making a callback from the kernel back to the user and giving the user a control at this point, saying, hey, if you want to do any action, do it. Once you're done, okay, I'm going to go and destroy this window. So everything looks fine till every process is behaving properly. But what if there is a malicious user who's trying to do something in this callback now? He's not going to play easy. He's going to play dirty at this point. What he does is, instead of actually doing something normal, he goes ahead and make a call to the destroy window again directly. And at this point, with this destroy window function in the kernel thinks, okay, I have already made a user mode callback. I don't have to make a callback again. Let me go ahead and destroy the window. So what it does is, it just removes the objects from the memory. And this is an awesome opportunity now, because you see, in the call stack, there is still a reference to that memory location. We haven't reached there yet. So what this guy is going to do during this callback, he's going to call a different function which say creates menu. So this is another object which is going to be created. And somehow he used his feng shui or whatever mechanism to get his menu object allocated in the exact same place where Windows object was allocated before. So typical use after free scenario. And when you end up getting back into this function call, which is the kernel mode destroy window, which was having a reference on the stack to a Windows object, is now referencing to menu object. And obviously, if it referenced now, it's going to cause all sort of problems. So how do we actually fix this? I mean, in the Windows world, like this is we know about this problem. This is not something unknown to us. So from coding perspective, we know that whenever we make a callback, we do something extra. What we do is we put a lock on the object, which means, hey, before I actually go and make a callback, let me put a lock so that this object will never go away until I unlock it again. So that way, my function can guarantee that, hey, no matter how many callbacks I made, because I have locked it, it's never going to go away because system is not going to delete it. That way, how you can solve this problem. I mean, that's the ideal scenario, but obviously, it's a code that you have to check by yourself. Like you should be aware of when you're writing this code that, hey, I need to put a lock and I need to unlock once I'm done with it. And obviously, it doesn't always happen. So that means there are always going to be bugs like this in the system. So, just to understand this a bit, Win32k is a very stateless system. And what I mean by that is, Win32k doesn't know what kind of state is it at a given point. It has to do validation at every given instance. So when it makes a callback, either it has to make sure that, hey, I'm making sure that whatever I'm working on is going to stay like this when I am back from this callback. Because callback can do anything. It can do any kind of damage. Or it has to revalidate everything after the callback is returned. So those are the stances that you need to take as a part of the code itself, because there is no state that is being maintained. And obviously, this is a complex problem, because anything can happen during that callback. Literally, like once you are out of the kernel context and in the user mode, you can do anything. You can pretty much call any system calls and make the system unstable, delink some of the windows and all that stuff. So you have complete control at that point. It becomes a lot more difficult for user Win32k code to keep track of everything going around. And obviously, as we see, use after free bugs pops up because of these kind of design things that have gone in the picture. And when use after free happens, that gives you one of the cog on the exploit machine that we were looking at, which is the memory corruption bug. So what is the solution to this? We set, like I said a couple of years back, thinking about, okay, this is a pretty prominent problem. What do we do for it? And obviously, we have to still work on the two pillars that I mentioned, the perf and the app compat. So we cannot absolutely break this feature. So what we said, okay, let's think about memgc. It's actually pretty easy or pretty fun way to do the exact same thing. It's going to make sure that the stack references are sane. If you try to destroy some object and if there is a reference on the stack, then I'm not going to destroy it, let you destroy it. I'm going to wait on it. So we thought about it, how are we going to introduce memgc in the picture? It was a very complicated story. We end up really figuring out that memgc is going to be very complex to do in kernel. There is no precedence to that today. So we went on the board and went back on the board and thought, okay, there are more ways to do it. Let's do it something called stack reference tracker. And let's think of it this way. So we have an object which is already created for you, and there is a kernel stack. Every time you create a reference to that object like this, we make sure that we know what references are being kept on the kernel stack through the object itself. So object is now extended to carry another linked list. And the linked list is going to keep increasing every time you create an object on the kernel stack. So at any given moment, the object knows what references are there on the kernel stacks. And this is not just the one stack, this is just a view of it. There are multiple stacks that can also be there, and every stack it's gonna keep a reference the way it is being kept right now. And what's gonna happen if I destroy the object? So before destroying the object, I do one action, which is I walk through the whole kernel, whatever the list that I've created, and start nullifying them. What does it give me, like as an opportunity? What it means is, now, while I'm destroying this object, I'm also wiping out all the references on the stacks, which means the next time if there is use after free, or if you start to use that reference, it is already nullified. It doesn't exist. And you might end up doing a null dereference, which will still result into a denial of service, a DOS basically, or a blue screen of death. But it's not going to make your exploit work anymore, because we have stopped you from referencing it to actual memory location. And here are some of the objects that we enlightened in with, like menu object and pop-up. We actually took a dig at, hey, what are the most common objects which have been used in this for this kind of exploitation, and we add up those this mitigation for those objects. More objects are getting added based on opportunity as it arises. And obviously the impact is we were looking at code execution at some point. This mitigation converts the code execution into denial of services. So it's a complete transformation from that perspective. And this makes the bugs unexploitable from that standpoint, because you can't exploit this anymore. So the third piece we were looking at is the shared data. So shared data is actually very common between user and kernel mode space. A lot of drivers uses it to transfer data in back and forth. But Win32k has some very unique requirements. So two requirements that I've listed here are handle tables and desktop heap. Now handle table, if you have ever worked on Win32 API space, you know you actually don't deal with pointers anymore. All you get is handles. Handle to a window, handle to a menu, whatever you get back from an API is an handle. And what does handle means? It's actually, handle is just an index into some table that we carry, which actually has the actual pointers to the objects. And that is the handle table we are talking about here. And desktop heap is something that we are sharing just for sheer optimization, where we say, hey, we are going to share some of the objects from Win32k.sys to the user so that user can run some optimization and make things faster. So we'll talk about this a little more in the next slide. So for example, this is what the system looks like. So you have a handle table, which is in the kernel. It is holding the kernel pointers to actual objects for a given handle. Apparently, we also share it with user mode. And the reason why we do it is to give an opportunity for user to make basically understanding of whether a handle is valid or not. It doesn't have to actually go into the kernel mode to make that assumptions. So it can, because the view is shared, it's a read-only view, but it's still shared. So user can actually take a look at it and say, oh, I know this handle is invalid, so let me not make a context switch and just go back to the application saying, hey, give me another handle, this is not valid. So this is for optimization again. And then there are obviously objects which are all over the pool memory, which are being referenced in the handle table. And there is some set of objects are being shared back to the user mode through something called desktop heap. And why do we do that again? Again for optimizations. In case you want to know, hey, I'm trying to send a message to a window, process might want to know, hey, is this window my parent window or not? So for that, it doesn't have to actually make a context to the kernel. Instead, it can look at the desktop heap, and use that as a primer and make that decision whether, hey, should I actually send it to which window, or should I even send it or not in the first place. So that's why we have this by design. These are for optimization. But apparently, they also do something interesting. They also leak pointers, kernel pointers, which was really sacred at some point. Like right now, we want to make sure nothing is leaked back to the user, but they are. By design, it's actually leaking these. What does it mean? Okay, so why? Oh, I've already talked why, so I'm going to just run through this. What does it mean? Why are we leaking these pointers? And what does it mean from security standpoint? Well, there is a cog that we talked about, the KSLR bypasses. KSLR is about, hey, do I know how the layout of kernel looks like? And if I end up sending all these content back to the user by default, then that cog is non-existent. That means you're already getting that cog even without finding any bug in Windows system. So there is a by design leaks of pointers because of the features that we have added in this Win32k subsystems. So how do we fix it? Like, I mean, we would have thought about, hey, okay, we could have easily removed this. It is not necessary. What's the point of having giving this control to the user? We thought about this, and then we said, hey, it's not that easy. We have pillars that we need to worry about, like the perf and the regression pillars. And obviously, we can't just remove it. So we have to work around it. And this is what the work we did. So we thought, okay, we know this thing is needed. What we can do is instead of sharing pointers, we can share offsets, which will give them what they want, but won't actually give them the pointers or the idea of how the kernel memory is laid out. So then obviously, we have to split few things, like the kernel table is actually split into two halves to do that, where one portion carries the portion which is shared, which can go fine, which has offsets, but the second portion contains the actual kernel pointers, because that is also needed by the kernel, because we don't want to touch too much functionality at the end of the day, because everything is still needed. Similarly, if you think about it, now the offset is still trying to get to the desktop heap, because desktop heap is still necessary for optimization. Like I said, we still have to keep the perf running the way it was. So the way we managed was, like, we know the offset is now the offset into the desktop heap itself. Earlier it was pointer, now it is an offset, which gives us benefit, like unless you know the actual base address of this desktop heap, you wouldn't actually know where the actual allocation of this object has gone through. Similarly, for the desktop heap, where there were pointers around, because an object can actually carry pointers to different objects, or it can actually have function pointers. So we don't want those things to be going back to the user mode. So we do the exact same thing which we did with the kernel handle table. Strip out the content which is not necessary, split into two halves, one which is fine to share with the user, one is not, and we're going to keep that in the kernel itself. So it looks fine on paper, but it's a very complex thing to actually make it work, because we don't want to change, again, we don't want to change too much code on the underline. So we had to use C++ primitives like smart pointers, which can make a decision, okay, am I going to go in this exclusive portion, or I'm going to go into the like a shared portion. And apparently Win32k was not written in C++ that much. It was very much written in C. There was some portion in C++. So we have to lift the code up a bit to make sure it works in C++ environment, which was a huge pain. I mean, like I said, it took us a couple of years to get here, so it definitely has gone through a huge code changes cycle. All right, functionally, we managed to get very minimal perf hit. We had 0 upcompat. If there was any upcompat, we actually went ahead and fixed and optimized the code back again. From security standpoint, we end up making a situation where there's no kernel pointer being leaked. So there is no by design KSLR bypass anymore. And we end up making fewer changes from kernel standpoint. And that helped because of the C++ stuff we added. You may ask about metadata which goes in the heap, because we also thought about it, because metadata contains flink and blinks, which are again kernel pointers. So what do we do about it? Well, there's something called that came out during the same time period we were working on this, something called segmented heaps, which actually carry all the metadata into the first page itself and doesn't share anything afterwards. And we actually end up using that to make sure none of this is maintained. So what's next? I'm just going to conclude this. We're already running out of time on this. So we did a huge redesign from a security standpoint. We took a decision like, hey, okay, security is important. We want to make that work for us. It was not easy, but it was a decision we took. It took us a while to get here, but we stick around. And at the end of the day, what we end up gaining is, this year, Pwn2Own, there was 0 Win30k bugs, which was a huge win. That doesn't mean that you can't still write Win30k bugs. You can still probably do it. It's just the cost is much more higher. So people are gonna probably go into the next thing. And the next thing is really what I have listed here, which is DirectX. Is getting a lot of love this year, which was one of the drivers which was totally owned during the Pwn2Own competition. And this is the next beast we are planning to tackle. And hopefully we'll have another story to tell next time I come here. So with that, here are some references for all the awesome work people have done, which will give you an idea of, hey, what I've gone through. This is not just me. This is a lot of researchers that have gone through and done a lot of work around Win30k. So take a look at it if you can. And that's it. That I'm going to conclude my presentation. And if you have any questions, feel free to ask. We have like